9,000 years ago, the largest hot desert on Earth did not exist. In its place stretched a world so alive, so watered, so full of movement that the sand beneath it today holds the bones of animals that have not lived in this region for millennia. Where the Sahara now bakes under relentless sun, there was grass, there were trees, there were rivers wider than the modern Mississippi threading across the landscape in every direction, connecting valley to valley, people to people, all the way from the Atlantic coast to the Nile. And at the center of it all, there was a lake, not a puddle, not a seasonal flood, a lake 150,000 square miles across, about 390,000 square kilometers, larger than every single one of North America's Great Lakes combined. In places, it reached 173 meters deep, nearly 600 feet, cold and dark at the bottom, teeming with life at the surface. Hippos slept with their backs above the waterline along its shore. Crocodiles held still in the shallows. This was not a different planet. This was the Sahara, the same Sahara. On cliff walls across this world, hands were pressing pigment into rock. Giraffes, crocodiles, cattle, people swimming, painted with the casual accuracy of people recording what was simply around them. Ordinary life, nothing worth explaining. Then it all began to disappear, not over countless ages, not so slowly that nobody noticed, fast enough for an entire landscape to unravel within the span of human lives. The mechanism that ended it, the thing that made it collapse faster than the physics governing it predicted, is one of the most disturbing findings in modern climate science. Today, we're returning to the Green Sahara to uncover the world that once flourished here, how it vanished with astonishing speed, what mechanism pushed it beyond the point of recovery, and why researchers believe that same process is still unfolding in parts of our world today. But before we do, if you're enjoying documentaries like this, a quick like and subscribe goes a long way. It really helps support the channel and allows us to keep bringing stories like this to life. Now, let's return to a time when the Sahara was green. Scientists have given this vanished chapter of North African history a formal name, the African Humid Period. It describes an interval that began around 14,800 years ago and continued until roughly 5,500 years ago, with its fullest expression between 9,000 and 6,000 years ago. Those dates mark far more than a change in rainfall. They define a time when one of Earth's harshest landscapes entered an entirely different ecological state, creating conditions that shaped plants, animals, and human communities across an immense region. Calling it the Green Sahara offers an easy mental picture, though the reality carried much greater variety. Great sweeps of grassland blended into shrubland. Woodland gathered wherever soils and water favored deeper roots. Marshes spread around lakes, while rivers wound across broad plains before joining larger drainage systems. Each environment merged into the next, forming a patchwork that shifted with local rainfall, elevation, and seasonal flooding. Diversity, rather than uniformity, became the defining feature of the landscape. The reach of this transformation was extraordinary. Fertile environments stretched from the Atlantic coast eastward to the Red Sea, and from the Mediterranean shoreline south toward the tropical belt. Across the full width of North Africa, living systems connected places that today seem impossibly distant from one another. Water carried nutrients, seeds, fish, and sediment across the land, while plants anchored soil that would eventually become exposed to relentless winds. Migration routes opened naturally for wildlife and for the people who followed them. Although this humid age feels unique from a human perspective, geology tells a much longer story. Sediment records extending back around 9 million years reveal that the Sahara has passed through hundreds of alternating green and desert phases. These changes unfolded with remarkable regularity across deep time, each humid interval rising and fading before another eventually followed. The African Humid Period remembered today represents only the latest complete chapter in an ancient rhythm that began long before humanity appeared to witness it. Confidence in this reconstruction rests upon many independent lines of evidence that converge toward the same conclusion. Ocean sediment cores preserve layers of dust and organic material carried from the continent. Ancient lake beds retain traces of changing water levels and aquatic life. Fossil bones reveal which animals occupied the region. Pollen grains record the plants that released them into the air. Deoxyribonucleic acid recovered from ancient remains adds another layer to the picture, while tens of thousands of rock paintings provide vivid glimpses of everyday life across landscapes that no longer exist. Each source tells only part of the story, yet together they reinforce one another with striking consistency. A shoreline identified in lake sediments matches animal remains found nearby. Vegetation reconstructed from pollen aligns with the scenes painted across cliff walls. Ocean records reflect the same broad environmental shifts preserved on land. Separate disciplines, working with entirely different materials and methods, repeatedly arrive at the same conclusion. For that reason, the African Humid Period stands among the best documented climate events preserved anywhere in Earth's geological history. The evidence does not depend upon a single remarkable discovery or one influential study. It emerges from countless observations gathered across decades of research, revealing that the familiar Sahara is only one expression of a landscape that has worn many different faces across the passing ages. Water shaped this landscape with such abundance that its traces still remain written across the continent. At the center of that watery world lay Lake Mega Chad, the enormous ancestor of today's shrinking Lake Chad. During its greatest extent, this inland sea covered more than 390,000 square kilometers, which is about 151,000 square miles. That made it even larger than the Caspian Sea, the largest lake on Earth today, where drifting dunes now dominate the horizon. Waves once stretched toward distant shores beyond ordinary sight. Its depth matched its astonishing scale. In some regions, the lake reached more than 183 meters, which is about 600 feet. Sunlight faded long before reaching the bottom, while broad shallows around the edges nurtured fish, reeds, and countless forms of freshwater life. Looking across its surface would have resembled standing beside an inland ocean instead of a desert basin. Even now, modern satellite radar can detect faint shoreline ridges surrounding the basin, preserving the outline of water that disappeared thousands of years ago. Beyond this immense lake, the rest of the Sahara carried water through an intricate network extending across nearly the entire region. During 2011, researchers publishing in the Proceedings of the National Academy of Sciences combined geological evidence with satellite observations to reconstruct chains of rivers, wetlands, and interconnected lakes spanning much of North Africa. Water moved from one basin into another, linking habitats across remarkable distances and creating continuous ecological corridors that supported life from one horizon to the next. Many of those rivers have long since vanished from the surface, although their pathways remain surprisingly clear from above. Dry channels known as wadis branch across the desert in graceful patterns, their courses still visible in satellite imagery. They cross plains that have not carried flowing water for thousands of years, preserving the memory of rivers that once gathered seasonal rainfall and guided it toward larger basins. Their shapes reveal sustained flow over immense spans of time, carving channels that could never have formed through rare storms alone. Far to the east, the Nile also carried the imprint of this wetter world. Increased rainfall across North Africa poured additional water into the river, strengthening its flow all the way to the eastern Mediterranean Sea. The fresh water entering the sea reduced oxygen levels in the deeper waters, allowing dark layers rich in organic material to accumulate on the sea floor. These deposits, known as sapropels, remain preserved within marine sediments, marking humid intervals with remarkable precision and providing one of the most dependable chronological records of changing African climate. Even the water that disappeared from the surface never entirely departed. Deep underground, enormous aquifers still store rainfall that soaked into the earth during the African Humid Period. Countries including Libya and Egypt draw upon these ancient reserves to support agriculture across otherwise arid regions. Every well tapping those buried waters reaches into a reservoir created by storms that fell thousands of years ago, replenished so slowly that each withdrawal removes part of an inheritance from another age. Across the Sahara, lakes vanished, rivers dried, and wetlands faded into sand. Even so, the framework they created never disappeared completely. Shorelines remain etched into the land, river valleys linger beneath the dunes, marine sediments preserve distant floods, and groundwater continues its patient journey through buried rock. The living water has gone, though its architecture still endures, allowing the landscape to remember the world that once flowed across it. Life announced itself across the African humid period in countless forms, filling every layer of the landscape with movement. Hooves crossed open grasslands, wings passed overhead, and broad waterways carried creatures that today survive far beyond the desert's reach. Reading the fossil record from this time resembles opening a field guide to a thriving savanna, except the locations attached to those discoveries belong to places now known for scorching rock and drifting dunes. Among the most striking inhabitants were hippopotamuses. Their massive bodies occupied lakes and river channels extending far north of their present distribution. Excavations deep within the Libyan desert have uncovered hippo bones resting in places where standing water has long disappeared. Those remains belong to animals that depended upon permanent fresh water throughout their lives. Their presence confirms that broad aquatic habitats once reached regions now counted among the driest on Earth, preserving evidence that no passing flood could have supported such creatures for generations. Sharing those waterways were crocodiles, patient hunters that required dependable rivers and stable shorelines. They occupied channels and lake margins across the Sahara, inhabiting environments that today offer little beyond cracked earth and shifting sand. Their fossils appear beside those of fish and other freshwater species, creating a consistent picture of ecosystems sustained by abundant water. Every discovery strengthens the conclusion that these predators lived within enduring habitats rather than isolated pools left behind by seasonal storms. Away from the water's edge, taller vegetation supported another familiar silhouette. Giraffes wandered through wooded savanna stretching across modern Libya, Niger, Chad, and Mali. Their browsing habits required scattered trees growing across extensive landscapes, while nearby herds of elephants, rhinoceroses, antelopes, gazelles, wildebeest, zebra, warthogs, and water buffalo grazed or browsed according to their own ecological roles. Each species occupied a different niche, together creating a balanced community whose diversity rivaled the wildlife found across East Africa today. The lakes themselves held another world. Catfish glided through deeper channels, while Nile perch pursued smaller prey. Tilapia flourished in calmer waters, accompanied by freshwater turtles moving between reed beds and open shallows. Their bones have been recovered hundreds of kilometers, which is about 124 miles, from the nearest permanent freshwater existing today. These discoveries remain among the most astonishing finds in Saharan paleontology because they place aquatic communities inside landscapes where fish could no longer survive without entirely different climatic conditions. Animals also endured in another archive, preserved by human hands instead of sediment. The Cave of the Swimmers in the Libyan desert contains paintings created around 9,000 years ago. Human figures appear stretched across the rock as though floating through water, surrounded by a setting that now receives almost no rainfall. Nearby images include wildlife familiar to a flourishing landscape, offering visual testimony that complements the fossil evidence recovered across the region. Farther southeast, the Manda Gweli Cave in the Aneti Mountains of northeastern Chad carries another collection of paintings. Its walls depict cattle moving together and hippopotamuses inhabiting nearby waters. Today, those same cliffs overlook exposed stone shaped by aridity, creating a striking contrast between the living scenes recorded by artists and the environment surrounding the artwork. Taken together, bones, paintings, and ecological evidence reveal a complete living system instead of scattered pockets of survival. Predators, grazers, aquatic life, reptiles, birds, and people all occupied connected habitats sustained by dependable rainfall. During the African Humid Period, the Sahara formed a species-rich ecosystem comparable in scale and complexity to the modern East African savanna, leaving behind records that continue to describe a world almost impossible to recognize beneath today's desert sky. As the rain settled into dependable rhythms, people arrived from many directions and discovered that this broad landscape could sustain more than seasonal journeys. Around 10,500 years ago, families began spreading across the Sahara in growing numbers, following lakes, rivers, and fertile plains that supported fishing, hunting, and eventually herding. Population reached its greatest density between 8,000 and 7,500 years ago, when communities flourished across a region that later generations would struggle to imagine as anything other than desert. One of the clearest records of these lives comes from Gobero in present-day Niger. Across roughly 5,000 years, the site became home to two distinct cultures, separated by a lengthy, dry interval when the nearby lake temporarily disappeared. The earlier inhabitants are known as the Kiffians, hunter, fisher, and gatherer communities living between 10,000 and 8,000 years ago. Around 1,000 years later, after wetter conditions returned, another culture known as the Tenerians established settlements in the same place, remaining until about 4,500 years ago. The Kiffians left behind skeletons that reveal unusually tall individuals, with some standing above 1.8 meters, which is about 6 feet. Their diet relied heavily upon fish, hippopotamuses, and other large animals supported by surrounding waterways. Harpoons crafted from crocodile and mammal bone became essential tools for daily survival. Many recovered examples have turned dark after spending centuries beneath waterlogged sediments, preserving a tangible connection to lakes that vanished long ago. Elsewhere, people expressed careful observation of the sky as well as the land. At Nabta Playa in southern Egypt, a Neolithic community assembled a stone circle around 7,000 years ago. The arrangement aligns closely with the sunrise at the summer solstice, making it one of the earliest known examples of megalithic architecture anywhere on Earth. Constructing such a monument required planning, shared knowledge, and cooperation extending far beyond the needs of a temporary campsite. Nabta Playa also occupied an important position within wider networks of exchange. Pieces of obsidian discovered there originated in the Ethiopian highlands, revealing journeys of many hundreds of kilometers, which is about many hundreds of miles, across connected landscapes. Other evidence links the settlement with communities in Sudan and Libya, showing that ideas and materials traveled alongside people. These exchanges suggest a world where movement followed established routes instead of isolated wanderings across empty terrain. The Sahara also witnessed the beginnings of a transformation that would shape much of African history. Around 9,000 years ago, the earliest evidence for cattle domestication on the continent appears within this flourishing environment. Herding gradually became central to daily life, turning grasslands into productive pasture. By 7,000 years ago, residues of ancient milk fats preserved inside pottery confirm that dairy production had become part of these communities, reflecting detailed knowledge of livestock and food preparation passed between generations. Another legacy spread across cliffs, caves, and rock shelters from Algeria through Libya, Niger, Chad, and Mali. Hundreds of thousands of paintings and engravings accumulated over centuries, creating what may be the greatest concentration of prehistoric rock art anywhere in the world. These images recorded herds, ceremonies, hunting, families, and familiar wildlife with remarkable confidence. Together, they reveal societies shaped by stable landscapes, sustained by cooperation, and connected through trade, belief, and shared memory. Long after villages disappeared, the stones continued carrying the record of the people who once called the Green Sahara home. Far inside Niger's Tenere Desert lies a place whose name has become inseparable from the story of the Green Sahara. The Tenere is often called the desert within a desert, a region so dry and isolated that reaching it remains a challenge even with modern equipment. Across its dunes, almost nothing hints that generations of families once lived beside fresh water. Only careful excavation revealed that an entire community had been resting there through thousands of years of changing climate. The discovery itself came by chance. During 2000, paleontologist Paul Sereno and his research team entered the area searching for dinosaur fossils preserved within older rocks. Human archaeology was never the purpose of the expedition. While crossing ancient dunes, scattered bones began appearing on the surface. Skeleton after skeleton emerged from the sand, their positions preserved with extraordinary clarity. Some jawbones still held tightly closed rows of teeth. One small hand projected upward with delicate finger bones still joined together. Harpoon points and broken pottery fragments lay nearby, scattered across the ground as though everyday life had paused only yesterday. Excavation gradually revealed the true scale of the site. Nearly 200 burials, spanning about 5,000 years of occupation, rested around the margins of an extinct lake. Together they form the oldest and largest Holocene cemetery known from the Sahara. Each grave contributed another piece to the history of the people who settled beside dependable water, raised families, and returned generation after generation to the same shoreline. Among these burials, one has become especially memorable. A woman lay beside two young children, their arms arranged around one another in an embrace carefully created before the grave was filled. The position remained undisturbed through thousands of years because the surrounding sediments hardened around them before the advancing desert sealed everything beneath drifting sand. The burial speaks through its arrangement without requiring any written language, preserving an expression of care within a landscape that today appears almost empty of human life. Objects placed with the dead reveal communities connected across considerable distances. Necklaces, fashioned from ostrich, eggshell beads, rested beside pendants carved from hippopotamus ivory. Other ornaments were shaped from blue amazonite, transported from outcrops in the Eyre Highlands, located several hundred kilometers away, which is about several hundred miles. Such materials reflect journeys, exchange, and craftsmanship extending well beyond the shoreline where these people lived. Gobero also carried every sign of an active settlement instead of serving only as a cemetery. Archaeologists recovered thousands of stone tools, together with abundant pottery fragments distributed across the site. Daily work, food preparation, fishing, and tool-making unfolded beside the same waters where later generations buried their loved ones. The rhythm of ordinary life surrounded the rituals of remembrance, creating a settlement that endured through changing centuries. Its survival depended upon an unusual source of water. The Paleo Lake beside Gobero received groundwater rising through a deep fault within sandstone formed during the age of the dinosaurs. This concealed aquifer continued feeding the lake even as rainfall varied from year to year, providing stability that attracted repeated settlement over long periods. Evidence from the lake itself completes the picture. Bones of crocodiles and large fish were recovered alongside the human burials, confirming the presence of permanent deep water in a region that now receives less than 2.5 centimeters, which is about 1 inch, of rain each year. Gobro preserves far more than human remains. It preserves the memory of an entire lakeside world, resting patiently beneath the sand that eventually replaced it. Standing in the modern Sahara, it is easy to imagine that the desert has always belonged exactly where it is. The geological record offers a very different perspective. Layer after layer of evidence reveals that the fertile world already explored was only the latest appearance in a repeating sequence stretching far beyond human memory. The Green Sahara emerged, faded, and returned many times before people ever walked across North Africa, following a rhythm measured across millions of years instead of individual civilizations. Ocean sediment cores preserve that rhythm with extraordinary fidelity. Beneath the floor of the Mediterranean Sea, scientists have recovered long cylinders of layered mud extending backward through time. Within those layers appear dark bands unusually rich in organic material. These deposits are known as sapropels. Each one formed during an interval when northern Africa received abundant rainfall. Rivers carried enormous amounts of fresh water into the sea, and biological productivity increased. Between those dark layers lie lighter sediments marking drier periods, creating an alternating pattern repeated again and again. Tracing these sequences deeper into the record carries the story at least 9 million years into the Miocene epoch. Hundreds of humid intervals appear within the sediments, separated by recurring desert phases. Their spacing follows a remarkably regular cadence, approximately one every 20,000 years. Such consistency cannot be explained through chance alone. The pattern remains visible across enormous spans of geological history, surviving changes in coastlines, ecosystems, and even the evolution of entirely different groups of animals. That repeating interval points toward a physical process operating beyond Earth's atmosphere. The timing matches a slow astronomical cycle known as orbital precession. Scientists reached this conclusion by comparing sediment records, astronomical calculations, and climate evidence from many different regions. Each line of investigation reinforced the others until the relationship became one of the clearest examples of orbital influence on climate preserved anywhere on the planet. Orbital precession describes a gradual change in the orientation of Earth's rotational axis through space. The motion resembles the gentle wobble of a spinning top, although the movement unfolds across many thousands of years. As the axis changes direction, the timing of Earth's position around the Sun shifts relative to the seasons. That subtle adjustment alters how much summer sunlight reaches northern Africa, influencing the strength of seasonal rainfall across the continent. Because this astronomical motion proceeds with remarkable regularity, the Sahara itself follows a repeating cycle instead of occupying one permanent state. The desert seen today represents only the present phase. Around 6,000 years ago, the region supported extensive ecosystems and thriving human communities. Around 12,000 years from now, calculations indicate that conditions favoring another humid interval are expected to return once more. Across geological time, the landscape oscillates between greener and drier expressions as the orbital rhythm continues without interruption. Recognizing this pattern changes the way the Sahara is understood. Its transformations belong to a predictable sequence governed by celestial mechanics rather than isolated accidents. The evidence preserved within sapropels, fossil records, ancient lakes, archaeological discoveries, and orbital calculations all converge toward the same conclusion. The great surprise is no longer that the Green Sahara existed. The greater mystery emerges from the pace of its ending. An astronomical cycle unfolding across roughly 20,000 years should encourage equally gradual environmental change. Yet, the geological record eventually reveals that one of these transitions unfolded with startling speed, departing from the gentle tempo established by the orbital clock that had guided the desert for millions of years. The rhythm preserved within sediments begins far beyond the atmosphere in the slow motion of Earth itself. Our planet does not spin with its axis standing perfectly upright. Instead, the axis leans by about 23.5 degrees and traces an almost imperceptible circle through space. The movement resembles the gentle wobble of a spinning top after it has been set in motion, except this celestial motion unfolds across roughly 21,000 years, guided by the combined gravitational influence of the Moon together with Jupiter and Saturn. This gradual shift is known as orbital precession. Although the motion is subtle, it changes one important detail of Earth's yearly journey. The point where Earth passes closest to the Sun slowly drifts through the calendar over thousands of years. Today, that closest approach arrives during January, when the Northern Hemisphere experiences winter. Thousands of years ago, during the African Humid Period, the timing was very different. Earth reached its nearest point to the Sun during July, placing northern Africa under stronger summer sunshine. The increase was modest at first glance. Summer sunlight across North Africa rose by roughly 7% compared with the present day. That difference may appear surprisingly small, yet land responds efficiently to additional energy. The Saharan surface warmed more intensely through the long summer months, creating broad regions of heated air rising above the continent. As warm air ascended, atmospheric pressure near the surface declined across much of northern Africa. Air naturally flows toward areas of lower pressure. Moisture-laden winds from the tropical Atlantic Ocean responded by pushing farther inland than they do today. As that humid air traveled across the warming continent, it climbed higher into the atmosphere, cooled, condensed into clouds, and eventually returned as rainfall. This seasonal circulation is known as the West African monsoon. During the African Humid Period, it expanded hundreds of kilometers beyond its modern limit, which is about hundreds of miles, carrying dependable rain into regions now lying deep within the central Sahara. The response of rainfall proved much greater than the increase in sunlight alone. Climate calculations indicate that roughly 7% more summer solar energy produced somewhere between 17% and 50% more monsoonal rainfall, depending upon how interactions with nearby oceans are represented within the models. A relatively modest astronomical adjustment, therefore, generated a remarkably different environment across North Africa, transforming dry plains into landscapes capable of sustaining rivers, lakes, wildlife, and growing human populations. Even so, another puzzle remained. Computer simulations that include only the orbital changes consistently produce conditions wetter than today. Yet they still fall short of recreating the extraordinary richness documented by geological and archaeological evidence. The modeled lakes remain too small, vegetation spreads too little, and rainfall never fully reaches the levels recorded by sediments, fossils, and ancient shorelines. That persistent gap has guided decades of research. The orbital wobble clearly established the foundation by directing stronger summer sunshine toward northern Africa and strengthening the seasonal monsoon. Something within the landscape itself, however, was adding further momentum to the process, allowing rainfall to spread beyond what orbital mechanics alone could sustain. The sky and the land were working together through a partnership more powerful than either could achieve independently, shaping one of the most remarkable climate transformations preserved anywhere in Earth's history. Once the rhythm of orbital precession becomes clear, another expectation naturally follows. If the amount of summer sunlight increased little by little, then its decline should also have unfolded little by little. Rainfall should have retreated across centuries, perhaps even millennia, giving lakes time to shrink gradually, vegetation time to adjust, and ecosystems time to reorganize. The astronomical clock described a measured progression, changing at a pace almost impossible to notice within a single human lifetime. The calculations support that expectation. Earth's orbital geometry shifted steadily, without abrupt leaps or interruptions. Each generation would have inherited almost the same amount of summer sunlight as the one before it. The process resembled a lamp whose brightness is lowered by tiny increments over thousands of years, producing changes so slight that they become apparent only after immense spans of time. Every known aspect of orbital forcing suggested that the African Humid Period should have faded with equal patience. The geological archive tells a different story. Marine sediments collected from the eastern Atlantic preserve an unexpected record of what actually happened. During 2000, researcher Peter Domenical and colleagues examined a sediment core recovered from Ocean Drilling Program Site 658, Charlie, located off the coast of Mauritania. Winds crossing northwestern Africa continuously carried fine Saharan dust into the Atlantic, where it settled layer upon layer across the seafloor. Those layers formed a natural history book recording how much exposed ground existed on the continent through time. When vegetation covered the Sahara, relatively little dust reached the ocean. Plant roots stabilized the soil, while rainfall suppressed loose sediment before winds could lift it into the atmosphere. As landscapes became drier and more barren, dust transport increased. The amount of wind-blown material preserved within each layer therefore provides a reliable measure of changing environmental conditions across broad regions of North Africa. Within that sediment core, one interval stood apart immediately. Around 5,500 years ago, the dust signal rose sharply instead of gradually. The transition resembled a steep boundary rather than a long slope. The sampling resolution represented approximately 100 years for each measurable interval, allowing scientists to estimate the timing with considerable confidence. The increase appeared to occur within decades or, at most, a few centuries. Against the backdrop of a 21,000-year orbital cycle, that shift was astonishingly rapid. The implication reached far beyond a single sediment core. A slow astronomical driver had produced what appeared to be an almost instantaneous transformation of an entire landscape. The orderly pace expected from orbital mechanics no longer matched the environmental response preserved within the geological evidence. Somewhere between the changing sunlight and the changing ecosystem, another process had dramatically accelerated the transition. Additional studies reinforced that conclusion. Climate scientist Jessica Tierney and her colleagues examined leaf wax molecules preserved within marine sediments, using their chemical signatures to reconstruct ancient rainfall. Their findings pointed toward the same broad picture. Moisture across the African humid period appears to have declined abruptly instead of fading through a long, gradual descent. One researcher described the event as abrupt climate change unfolding on a scale that human communities could directly experience. The most widely cited estimates place the principal collapse within roughly 200 years, an interval brief enough for grandparents and grandchildren to witness the same world transforming into another. That striking mismatch between gradual forcing and rapid response became the central mystery of the Green Sahara. Far from the dunes themselves, the Atlantic Ocean preserved a record that no shifting wind could erase. Each grain of dust settling through seawater carried a fragment of the continent's condition, gathering layer upon layer across the ocean floor until mud became an archive extending back through thousands of years. The most revealing pages of that archive came from a location known as Ocean Drilling Program, Site 658, Charlie resting off the coast of Mauritania in the eastern Atlantic, around 1,900 kilometers, which is about 1,200 miles from the nearest Saharan dune fields. At that distance, the sediments reflected changes across an immense region instead of a single valley or lake. The Sahara continually releases mineral dust into the atmosphere. Trade winds sweep those particles westward across the Atlantic every year. During dry periods, exposed ground supplies enormous quantities of sediment, filling the air with fine grains that eventually descend through the water column onto the seabed. During humid periods, grasses, shrubs, and trees stabilize the soil, while rainfall binds loose particles before the wind can carry them away. Less dust reaches the ocean, and the accumulating sediments record that difference with remarkable clarity. Each layer formed gradually, often representing a century or more of continuous deposition. Scientists examined far more than the dust itself. Organic compounds preserved within the mud reveal the productivity of nearby ecosystems. Leaf wax molecules transported from the continent preserve chemical signatures linked to rainfall. Isotopes locked inside the sediments provide additional clues about changing environmental conditions. Read together. These lines of evidence transform ordinary ocean mud into a detailed history of climate across North Africa. The sequence below, roughly 5,500 years ago, tells a remarkably consistent story. Dust concentrations remain comparatively low. Organic material is more abundant. Chemical indicators point towards sustained rainfall and flourishing vegetation across much of the western and central Sahara. The Green Sahara appears plainly within the sediment, expressed without forests, rivers, or lakes ever being directly observed. The continent described itself through the particles it released into the sea. Then the pattern changes with startling speed. Above that boundary, dust levels rise dramatically. The increase resembles a steep wall, more than a gentle incline. Instead of a landscape responding gradually to slowly changing sunlight, the record suggests a threshold had been crossed. Within what appears to span only decades to perhaps a century or two, conditions shifted toward widespread aridity. The sediment preserves that transformation as a striking cliff within an otherwise orderly timeline. Evidence from leaf wax isotopes recovered in additional Atlantic sediment cores strengthens the same conclusion. Across broad portions of the western and central Sahara, rainfall appears to have declined abruptly, consistent with ecosystems reaching a tipping point instead of retreating evenly year after year. At the same time, records from the eastern Sahara often indicate a more measured drying, unfolding across a longer interval. That difference has encouraged productive scientific discussion instead of contradiction. Both patterns can exist within the same continental story. Regional climates rarely respond in perfect unison. One landscape may pass a critical threshold, while another continues to receive enough seasonal rain to endure for centuries longer. The Sahara's transformation, therefore, unfolded as a sequence of regional endings, each preserved within sediments that settled patiently onto the Atlantic floor, leaving behind one of the clearest physical records of a world changing far faster than its astronomical clock predicted. The turning point did not arrive from the sky alone. The gradual shift in Earth's orbit provided the first nudge. Yet another process already woven into the landscape determined how that nudge would unfold. Climate scientists describe this process as vegetation albedo coupling, a feedback loop linking living plants, sunlight, rainfall, and the land itself. Once the cycle gathered momentum, each change strengthened the next, allowing a modest astronomical adjustment to reshape an entire continent. Albedo is the scientific term for how strongly a surface reflects incoming sunlight back into space. Bright surfaces possess higher albedo because they return more sunlight instead of absorbing it. Pale desert sand is highly reflective. Grasslands, shrubs, and woodlands are darker, so they absorb a greater share of the sun's energy. That absorbed warmth heats the land above them, influencing air pressure and the movement of moisture across enormous distances. A change in ground cover therefore changes more than the appearance of a landscape. It alters how energy flows between Earth and the atmosphere. Around 6,000 years ago, the slow decline in Northern Hemisphere summer sunlight gradually weakened the West African monsoon. The reduction unfolded steadily, following the rhythm established by orbital precession. Rainfall first diminished across the northern margins of the Green Sahara, where vegetation already occupied the edge of what seasonal moisture could sustain. Those grasslands and scattered woodlands required dependable rains each year. As those rains became less reliable, the first plants withered, leaving increasing patches of exposed sand. Each new patch of bare ground reflected more sunlight than the vegetation it replaced. Less solar energy remained available to warm the surface. Cooler land reduced the temperature contrast between North Africa and the nearby tropical Atlantic Ocean. That contrast had powered the low pressure drawing moisture inland every summer. As the difference weakened, the atmospheric circulation feeding the monsoon weakened with it, allowing even less rainfall to reach the interior. The landscape had entered a self-reinforcing cycle. Reduced rainfall caused additional vegetation loss. Expanding areas of exposed sand increased albedo. Higher albedo reduced surface heating. Weaker heating diminished the inflow of moist air. Diminished moisture reduced rainfall again. Each step reinforced the next until the original orbital influence became only one part of a much larger chain of interacting processes. After a critical threshold had been crossed, the system increasingly sustained its own decline. Another amplifier joined the process. Plants normally anchor soil with roots, while leaves soften the force of wind near the ground. As vegetation disappeared, loose mineral particles became easier to lift into the atmosphere. Dust spread across the sky in greater quantities. Those suspended particles reflected part of the incoming sunlight before it reached the surface, leaving the land cooler still. Cooler ground further weakened the monsoon circulation, allowing additional dust to enter the air and continue the cycle. For thousands of years, vegetation and seasonal rainfall had supported one another across the Sahara. Rain allowed plants to flourish, and those plants helped maintain the warmth that strengthened the monsoon, bringing fresh moisture inland. When the balance shifted, the same partnership reversed direction. A system that had preserved a living landscape for millennia became the mechanism that accelerated its transformation, carrying gradual orbital change into a continental collapse unfolding within the span of human generations. Some changes in nature unfold so gradually that they seem almost motionless. Others remain restrained for long stretches, only to transform with startling speed after crossing a boundary that had remained invisible until the very last moment. Climate scientists have a precise term for this behavior. They call it a tipping point, a threshold within a complex system where a small, gradual change in an outside influence produces a sudden, much larger shift in the system itself. Once that threshold has been crossed, returning to the previous state can become difficult or even impossible because the internal processes now reinforce the new condition. The idea first emerged from mathematical studies of complex systems and has since become one of the central concepts in climate science. Forests, ice sheets, ocean circulation, and ecosystems can all display this behavior under the right conditions. Among the many examples preserved in Earth's history, the Green Sahara stands as one of the clearest and most thoroughly documented records of a tipping point unfolding across an entire continent. The evidence stretches through sediments, fossil pollen, archaeological sites, and climate models, each contributing another piece to the same physical story. A simple image helps describe the process. Imagine a table resting on a smooth floor. One edge begins to rise, almost imperceptibly. For a long time, every object placed upon the surface remains exactly where it is. The table continues to tilt, little by little, and still nothing moves. Then the angle reaches a critical point. Without any dramatic increase in the rate of tilting, every loose object begins to slide almost together. The gradual motion created the conditions. Crossing the threshold released the response. The Sahara followed a remarkably similar pattern. Orbital precession slowly reduced the amount of summer sunlight reaching North Africa over many centuries. That gradual astronomical change resembled the steady lifting of the table. Vegetation and rainfall adjusted at first without dramatic disruption. Eventually, the coupled system of plants, soil, moisture, and atmospheric circulation approached a critical limit. Once that limit had been exceeded, vegetation declined rapidly, albedo increased, rainfall weakened further, and the reinforcing feedbacks carried the landscape toward a much drier state far more quickly than the orbital change alone could explain. A study published during 2022 in the journal Environmental Research Letters reproduced this behavior using a climate model calibrated specifically for Holocene environmental conditions. The simulations showed vegetation remaining comparatively stable until moisture availability approached a critical threshold around 6,000 years before present. Beyond that point, plant cover diminished rapidly through interacting albedo and moisture feedbacks, closely matching the pattern preserved in geological evidence. The same investigation also identified smaller drying episodes around 7,250 years before present and 6,600 years before present. These temporary interruptions appeared before the final transition, suggesting that the system was becoming increasingly unstable while still recovering after each disturbance. During roughly the final 500 years preceding the principal collapse, fluctuations in vegetation became noticeably larger. Climate scientists now recognize this growing variability as a statistical warning that a complex system may be nearing a tipping point. Further support arrived during 2025 when researchers at the Technical University of Munich applied mathematical techniques developed specifically for climate systems. Their analysis detected a clear early warning signal before the rapid vegetation decline, strengthening the conclusion that the Green Sahara did not fade away through steady decline alone. It crossed a threshold, and the landscape responded with the unmistakable signature of a tipping point. Science rarely advances by collecting identical answers. It advances by placing different pieces of evidence beside one another until a broader picture begins to emerge. The story of the Green Sahara follows that same path. Although many researchers agree that the transformation from grassland to desert unfolded far more rapidly than the slow change in Earth's orbit, the precise speed of that transition remains an active subject of investigation. The discussion continues because different parts of the Sahara preserved different histories, each recorded in its own landscape. The strongest evidence for an exceptionally rapid collapse comes from the Atlantic margin west of Africa. Peter Domenico and his colleagues examined sediment recovered from the Mauritanian offshore dust record during 2000. Layer after layer preserved the amount of wind-blown mineral dust arriving from the continent. Around 5,500 years ago, the record shows a striking rise within a remarkably short interval. The increase appears so abrupt that many researchers interpret it as evidence that large areas of the Western Sahara shifted from vegetated land to exposed ground within decades to perhaps 2 centuries. Measured against geological time, the transition resembles a step instead of a slope. Evidence gathered farther east tells a different, though equally valuable, story. Research led by Stefan Krupplin examined lake sediments from northern Chad, where ancient shorelines and biological remains preserve a long environmental archive. Those records indicate that drying progressed over a much longer span, beginning around 5,000 years before present and continuing until roughly 2,700 years before present. In that region, lakes gradually contracted, vegetation retreated over many generations, and the modern desert ecosystem emerged only after an extended interval. The Eastern Sahara appears to have surrendered its greener landscape more gradually than the West. At first glance, these conclusions seem difficult to reconcile. One suggests an abrupt transformation, while the other points toward a prolonged environmental shift. Yet the Sahara covered an enormous region with varied landscapes, groundwater supplies, lakes, and vegetation. A continent-sized ecosystem does not always respond as though every valley and plain were connected by a single clock. Local conditions can delay or accelerate change while still responding to the same underlying climatic influence. Additional support for this interpretation arrived in a 2026 preprint from the Max Planck Institute. By comparing climate model simulations With multiple paleoclimate records, the researchers found that transitions inferred from Western Saharan dust archives appeared noticeably sharper than those reconstructed from pollen records, which generally preserved more gradual ecological adjustments. Their analysis suggested that both styles of evidence describe real processes occurring in different places and at different rates, rather than contradicting one another. Across this discussion, several conclusions remain remarkably consistent. Few climate scientists argue that the orbital change by itself could account for the observed pace of environmental transformation. The reinforcing interaction between vegetation, surface reflectivity, atmospheric dust, and monsoon rainfall is widely recognized as the mechanism that accelerated drying beyond the gradual pace of astronomical forcing. Likewise, there is broad agreement that the Green Sahara disappeared on timescales meaningful to human communities, and that, once established, the desert state endured far beyond the lifetimes of those who experienced its arrival. The debate concerns the details of timing across different regions, while the larger story remains firmly supported by the evidence. After tracing the forces of orbit, rainfall, vegetation, and feedback, another possibility enters the story with greater uncertainty. This one does not begin in the sky or in the physics of climate. It begins with people walking across grasslands beside their cattle, building lives within a landscape that had supported generations. Some researchers have asked whether those communities, without intending it, may have nudged an already fragile system closer to its breaking point. The idea remains a hypothesis, discussed seriously but far from universally accepted. During the height of the African Humid Period, human populations expanded across regions that had once been too dry to occupy. Pastoral societies moved with their herds through broad plains and seasonal grazing grounds. Many of these settlements reached the northern margins of the monsoon belt, where rainfall already balanced near the minimum needed to maintain continuous vegetation. Those borderlands represented the most delicate part of the ecosystem, where relatively small environmental changes could have larger consequences. Researchers, including David Wright, propose that repeated grazing in these marginal landscapes may have reduced plant cover enough to expose patches of bare ground. Once vegetation thinned, the brighter sandy surface reflected a greater share of incoming sunlight back towards space. That increase in surface reflectivity, combined with the gradual weakening of summer rainfall already driven by orbital change, may have encouraged the feedbacks described earlier. According to this interpretation, human activity did not create the drying trend, but it may have strengthened a process already underway, allowing the system to cross its threshold sooner or more completely than natural forcing alone might have produced. The proposal attracted considerable attention beyond academic journals. During 2017, the Smithsonian Institution published an article discussing the possibility under the title suggesting that humans may have transformed the Sahara from a lush paradise into a barren desert. The headline reflected the appeal of the idea, placing ordinary people alongside planetary forces in one of Earth's great environmental transformations. It also encouraged renewed examination of archaeological evidence from settlements scattered across the former grasslands. Many specialists remain unconvinced by that conclusion. Nick Drake and other researchers argue that archaeological discoveries point toward pastoral practices that generally matched the rhythms of the landscape instead of exhausting it. Herds moved seasonally, allowing grazing areas time to recover. Population declines also appear alongside the climatic deterioration instead of clearly preceding it. From this perspective, the people of the Green Sahara experienced the environmental collapse as participants caught within it, adapting for as long as conditions allowed, before eventually abandoning territories that could no longer sustain them. Further complexity emerged through a study published during 2018. Its findings suggested that pastoral communities may even have delayed environmental decline in certain regions. Careful management of grazing land could have maintained patches of vegetation that otherwise might have disappeared sooner, preserving moisture and reducing exposed sand in vulnerable areas. If that interpretation proves correct, human activity briefly resisted the feedbacks instead of accelerating them. For now, the question remains unresolved. The continuing debate reflects the challenge of separating the influence of climate from the influence of human land use across thousands of years. Whatever the final answer, the discussion reaches beyond the Green Sahara itself. It asks how people and ecosystems shape one another when a world already drifting toward a threshold begins to change. A changing climate can be measured in sediments, pollen, and dust, yet its deepest record often survives in the paths people leave behind. Across the Green Sahara, communities that had flourished beside lakes and grasslands entered a world becoming less dependable with each passing generation. The transformation unfolded across human lifetimes, carrying families farther from places their ancestors had known until familiar landscapes existed only in memory. Around 5,500 years ago, archaeological evidence from the Western Sahara records a steep decline in human occupation that closely matches the deterioration seen in climatic archives from the same region. Campsites that had once supported repeated visits fell out of use. Seasonal movements became longer, while dependable water became harder to find. The rhythm of daily life shifted with the retreat of rainfall, leaving fewer places capable of supporting permanent settlement. Gobro preserves one of the clearest endings. For thousands of years, its lakeshore had welcomed generations who fished, hunted, buried their loved ones, and shaped pottery beside reliable water. Then the Tenerian occupation came to an end. The cemetery received no further burials, homes disappeared, and the people never returned. Wind carried sand across the abandoned ground until every trace vanished beneath expanding dunes. That blanket of sand protected the site through thousands of years, preserving a chapter of human history until chance revealed it once more. Similar patterns appear across much of the Sahara. Archaeological sites were not abandoned all at once, nor did every region follow the same timetable. Even so, the broad direction remains consistent. Settlements gradually shifted toward the south and east, following the shrinking reach of the summer rains. Communities repeatedly established themselves where grass remained, only to move again as favorable conditions continued to withdraw across the landscape. The same story emerges at Nabta Playa in what is now southern Egypt. This remarkable ceremonial and astronomical landscape depended upon seasonal water that no longer arrived with its former reliability. Around 5,000 years before the present, evidence points toward the movement of both people and livestock away from the region as environmental conditions became increasingly difficult. The migration followed the remaining corridors where grazing, fresh water, and dependable seasons still endured. Ancient deoxyribonucleic acid, recovered from Saharan burials, has added another layer to this history. These studies indicate that populations living across the Green Sahara possessed distinctive genetic lineages during the humid period. Their descendants did not disappear with the grasslands. Instead, their ancestry became woven into later populations across sub-Saharan Africa, the Nile Valley, and North Africa, preserving biological connections long after the lakes themselves had faded. For the people living through these centuries, departure was rarely a single decision. Each move likely followed another season of weaker rains, another shrinking shoreline, another pasture unable to support cattle. Wells yielded less water. Familiar routes changed. Children grew up walking farther than their parents had once needed to travel. The catastrophe unfolded through countless ordinary choices, shaped by an environment losing its capacity to sustain life. As the monsoon retreated, the Egyptian Sahara experienced a progressive abandonment that guided many communities toward the Nile Valley. They carried far more than possessions. They brought established traditions of cattle herding, pottery making, careful observation of the sky, and social knowledge refined across generations in a greener world. Even after the desert closed behind them, those traditions continued their journey through the civilizations that followed. Rivers often gather more than water. They gather journeys already in motion, carrying together lives that began far beyond their banks. As the Green Sahara withdrew from one generation to the next, the Nile Valley became the destination toward which many of those journeys slowly converged, drawing people, traditions, and practical knowledge into a landscape that was becoming increasingly crowded. Archaeological evidence places this movement between roughly 5,500 and 5,000 years before the present, a span that closely matches a noticeable acceleration in the complexity of societies along the Nile. Earlier settlements had certainly flourished there, sustained by dependable floods and fertile ground. Even so, communities generally remained modest in size and organization. After populations began arriving from the drying Sahara, settlement density increased, craft specialization expanded, social differences became more visible, and exchange networks reached farther across northeastern Africa. Monumental construction also emerged with growing confidence, suggesting that larger communities were capable of coordinating labor on an entirely different scale. Several researchers, including Fakhri Hassan, have proposed that these developments were shaped by more than favorable environmental conditions. They argue that migrants from the former grasslands carried generations of experience acquired before the desert expanded. Their knowledge included cattle herding, pottery production, seasonal planning, long distance movement, and forms of social organization refined across centuries of life within a productive landscape. The Nile offered dependable water, while the newcomers contributed skills and traditions already tested through changing environments. One of the most intriguing connections reaches back to Nabta Playa. Its stone circle and carefully arranged monuments reveal sustained observation of the heavens long before the rise of pharaonic Egypt. Burials of cattle at the site suggest that these animals possessed ceremonial importance extending beyond their practical value. Later, Egyptian religion placed cattle at the heart of powerful religious symbolism, particularly through the goddess Hathor. Although direct ancestry cannot be demonstrated with certainty, the resemblance has encouraged continuing discussion among archaeologists studying cultural continuity between Saharan pastoral communities and the early Nile civilization. Material culture points in a similar direction. Cattle occupied a central place within the economy and identity of Green Sahara herders, and that emphasis aligns more naturally with early Egyptian symbolism than with earlier Nile communities whose traditions appear less strongly centered on pastoral life. Rather than representing isolated inventions, these religious and cultural themes may have developed through the blending of local Nile traditions with ideas carried by migrants arriving from lands that could no longer sustain them. Ancient deoxyribonucleic acid has added another piece to this growing picture. Genetic analyses of predynastic individuals from Egypt indicate meaningful ancestry connected to populations associated with the Green Sahara. These findings support archaeological evidence that movement into the Nile Valley involved substantial numbers of people instead of occasional travelers. Population growth therefore reflected both local development and the arrival of communities shaped by centuries of life across the former savannas. Many researchers now regard this as a compelling working hypothesis rather than a settled conclusion. The decline of the Green Sahara compressed population, knowledge, belief, and technical experience into the narrow ribbon of the Nile Valley. Within that corridor, interaction became more frequent, cooperation more necessary, and political organization increasingly advantageous. One of history's most celebrated civilizations may therefore owe part of its beginning to the disappearance of a landscape that had once seemed capable of enduring without end. A transformation on this scale could never remain confined to one horizon. Air moves across continents without recognizing borders, carrying heat, moisture, and dust through a planetary network that binds distant landscapes together. As the African Humid Period faded between roughly 5,500 and 4,200 years before the present, changes that began across northern Africa gradually echoed far beyond the former grasslands. This span of time overlaps with one of the most turbulent chapters in early human history. Across several regions, societies reorganized, settlements shifted, and political systems faced growing strain. The timing alone does not prove that every change shared a single cause, yet climate records increasingly suggest that many of these events unfolded within the influence of a broad environmental transition. The disappearance of one of Earth's largest vegetated regions altered atmospheric circulation on a scale capable of affecting climates thousands of kilometers away, which is about 1,864 miles. One of the clearest examples appears in Mesopotamia. Around 4,200 years before the present, the Akkadian Empire, often described as the world's first empire, entered a period of rapid decline. Geological evidence points to a prolonged drought associated with what scientists now call the 4.2 kiloyear climate event. Dust deposits increased, agricultural production faltered, and settlements were abandoned across parts of the Fertile Crescent. Although political pressures and social tensions also played important roles, climate became an unmistakable part of the story. Climate modeling has strengthened the connection between these distant regions. During the Green Sahara, vigorous seasonal rains recycled enormous amounts of water back into the atmosphere through vegetation and evaporation. That moisture helped sustain circulation patterns extending into West Asia and the Middle East. Once the monsoon weakened and vegetation retreated, the atmospheric supply of moisture diminished as well. Dry conditions that had begun across northern Africa became linked with broader shifts affecting neighboring continents. Farther east, the Indus Valley civilization experienced its own profound transformation during the same climatic interval. Urban centers that had supported large populations gradually gave way to smaller settlements distributed across a wider landscape. Research attributes much of this transition to a long weakening of the monsoon system, reducing dependable rainfall over South Asia. The changing atmosphere influenced river systems, agriculture, and the rhythms upon which cities had depended for centuries. The pattern extends even farther. Research published in Nature Communications during 2020 concluded that the termination of the Green Sahara intensified mid to late Holocene megadroughts across mainland Southeast Asia. These findings emphasize that northern Africa functioned as part of an interconnected climate engine rather than an isolated regional phenomenon. Variations in African vegetation altered atmospheric circulation, reaching from the Atlantic Ocean toward the Pacific, reshaping rainfall far beyond the desert itself. By this stage, the Green Sahara had become more than a memory within Africa. Its disappearance reduced moisture recycling across one of the planet's largest continental regions, allowing dust, shifting winds, and weakened monsoons to influence climates across three continents. The loss of that living landscape became woven into a broader chapter of human history, leaving traces in collapsing kingdoms, changing rivers, migrating communities, and skies that no longer carried rain along familiar paths. Stone has an unusual way of keeping memories. Long after forests disappear, rivers change course, and voices fade from the places where they once echoed. Marks left upon rock continue waiting for another pair of eyes. Across the Tassili Niger Plateau in southeastern Algeria, now recognized as a United Nations educational, scientific, and cultural organization World Heritage Site, thousands of paintings remain scattered across cliffs, shelters, and overhangs. Together, they preserve scenes from a landscape that vanished long before written history began. The modern world first learned of many of these images through the travels of the German explorer Heinrich Barth. During the 1850s, he crossed the Sahara by camel caravan from Tripoli to Timbuktu, recording paintings that seemed impossible to reconcile with the country surrounding them. He found giraffes stretching their necks toward branches, cattle gathered beneath attentive herders, hunters carrying bows, and figures whose daily lives appeared tied to abundant water and vegetation. To observers familiar only with shifting dunes and exposed stone, these images resembled fragments of another continent. Subsequent research revealed that the paintings belonged primarily to the African Humid Period. Some were created as much as 12,000 years ago, when lakes reflected broad skies and grasslands supported large mammals across regions that today receive scarcely any dependable rainfall. Their artists were not imagining an unreachable paradise or illustrating legends handed down across generations. They painted what surrounded them, preserving familiar animals and familiar routines with remarkable confidence and precision. Among the most striking examples lies within the Cave of the Swimmers on Egypt's Gilf Kebir Plateau. The chamber became widely known through the motion picture, The English Patient, yet its greatest significance comes from the figures themselves. Around 9,000 years ago, artists covered the rock with human forms stretched horizontally, arms extended as though moving through open water. Today, the cave stands within one of the driest places on Earth. The swimmers remained suspended across the stone, continuing motions that depended upon lakes disappearing thousands of years ago. Elsewhere, the paintings at Monda Gali in Chad portray hippopotamuses with careful attention to posture, proportion, and movement. Such accuracy suggests close familiarity developed through repeated observation. These animals were companions within the surrounding environment, encountered along shorelines and waterways instead of existing as distant curiosities. Nearby panels also depict crocodiles and large herds of cattle in regions now receiving less than 1 inch of rain each year. The rock preserves ecological relationships that no longer exist across those landscapes. Every painted surface carries more than artistic expression. Each scene records practical knowledge of animals, seasons, and human life that flourished before climate reshaped the continent. Unlike bones or scattered tools, the paintings capture movement itself, revealing how people understood the living world around them while it still endured. The lakes disappeared, the rivers withdrew, communities followed the retreating rains toward new homes, leaving their shelters behind. The painted cliffs remained where they had always stood. Dry air, which gradually erased the ecosystems that inspired these images, also shielded the pigments from decay. Across the Sahara today, the surviving paintings continue to watch over an empty landscape, preserving the memory of a world that vanished while its portraits endured. The greatest map of the lost Sahara was never drawn from the ground. It emerged from far above, where instruments looking down upon the earth could perceive patterns concealed beneath countless layers of sand. From that distant vantage, the desert gradually revealed features that generations of travelers had crossed without ever seeing, preserving the outlines of landscapes, erased from ordinary view, but never fully removed from the land itself. During the National Aeronautics and Space Administration Shuttle Radar Topography mission, radar pulses passed through the dry surface sands across large parts of the Sahara and returned images unlike anything expected. Instead of recording only dunes and exposed rock, the instruments traced buried valleys, forgotten shorelines, and sprawling drainage systems extending across the desert. These formations remained invisible at ground level, yet from orbit they appeared with remarkable clarity, as though another continent rested just beneath the modern one. Across the eastern Sahara, ancient river channels branch outward in intricate patterns, recognizable to every geologist. Their networks resemble the limbs of living trees, dividing again and again as streams once gathered into larger rivers. Some of these channels stretch for hundreds of kilometers, which is about hundreds of miles, maintaining shapes that could only have formed through sustained rainfall over many thousands of years. They were not temporary washes filled by occasional storms. They belonged to river systems, comparable in scale to the modern Niger River and the Nile, carrying dependable flows across landscapes now defined by extreme dryness. The same perspective also reveals the forgotten margins of Lake Megachad. Pale arcs curve across the terrain far beyond the shores of today's much smaller lake, marking former coastlines left behind as water steadily withdrew. They resemble faint rings left inside an emptied basin, recording successive stages in the shrinking of one of the largest freshwater bodies that ever occupied Africa. Those shorelines remain fixed within the landscape, even though the waves that shaped them disappeared thousands of years ago. Elsewhere, broad lake beds appear as level, pale depressions scattered across Niger, Chad, Mali, and Libya. Their surfaces preserve layers of fine sediment that settled through calm water before becoming sealed beneath wind-blown sand. Each basin represents another chapter of the vanished hydrological network that sustained animals, plants, and human communities across regions now receiving little more than traces of annual rainfall. The evidence reaches beyond geological structures alone. In 1987, a Fulani herdsman digging a well in northeastern Nigeria uncovered an object buried approximately 5 meters, which is about 16 feet, below the surface. It proved to be the Dufuna canoe, carved from African mahogany around 8,000 years ago. It ranks as the second oldest known boat in the world. Its builders crafted it for waterways that have long since disappeared, navigating lakes and channels that survive today only within buried sediments and ancient landforms. Seen from orbit, the Sahara becomes a landscape carrying two geographies at once. One belongs to the present, shaped by dunes, gravel plains, and relentless dryness. The other remains etched beneath the surface, preserved in river valleys, abandoned shorelines, lake basins, and forgotten waterways. The desert has not erased the world that came before it. It has covered that world with sand, leaving space-borne instruments to uncover the memory still written across the earth itself. A long story can contain an unexpected pause, a passage where the rhythm falters before finding its course again. The Green Sahara carried such a moment within its own lifetime. Long before the landscape reached its irreversible turning point, the rains weakened for a time, the lakes contracted, and communities stepped away from places that had once sustained them. The interruption did not end the humid world, yet it revealed that even during its flourishing, the system could waver. Evidence for this interruption comes from an unlikely archive resting beneath the Atlantic Ocean. Tiny traces of leaf wax, washed from African plants into marine sediments off West Africa, preserve changes in rainfall through shifts in their chemical composition. Those isotopic records reveal a prolonged reduction in precipitation centered around roughly 8,000 years ago. The interval appears to have lasted for perhaps a century or longer, leaving a recognizable break in otherwise favorable humid conditions across much of the region. On the shores of the former Gobero Lake, the same event appears through archaeology instead of chemistry. The Kiffian people, tall hunter, fisher, and gatherer communities who had lived beside abundant water, vanish from the record around this period. Their camps disappeared as the Paleo Lake retreated. Fish populations dwindled with the shrinking waters, and the familiar cycle of daily life could no longer continue. Gobero itself fell empty. For approximately 1,000 years, no people returned to bury their dead, shape tools, or leave hearths upon its shores. The lake was gone, the fish were gone, and human footsteps faded from the sediment alongside them. Eventually, the climate shifted once more. Seasonal rains strengthened, water collected again within the basin, and life returned along renewed shorelines. Those returning people belonged to an entirely different culture. Around 7,000 years ago, the Tenerian pastoralists settled the restored landscape, bringing cattle, new burial customs, and a different way of living with the recovering environment. Gobero became inhabited again, yet it was no longer the same community reclaiming an old home. The place endured while its people had changed. Comparable interruptions appear elsewhere across the Sahara. Archaeological sites from several regions record temporary abandonment during this dry interval, followed by renewed occupation when wetter conditions returned. Human settlement contracted southward as dependable rainfall retreated, then expanded once more when the monsoon regained strength. The pattern unfolded across broad areas, suggesting a continent responding together to a shared climatic disturbance rather than isolated local events. Viewed through the lens of climate dynamics, this episode resembles a rehearsal for what would come much later. The same feedbacks linking rainfall, vegetation, and surface reflectivity were already active, although they unfolded on a smaller stage. Vegetation diminished, moisture recycling weakened, and drying spread through connected landscapes. Even so, the broader climate still favored humid conditions. Orbital forcing continued to support the summer monsoon, allowing rainfall to recover before the system crossed its ultimate threshold. That distinction proved decisive. During the earlier interruption, the larger climatic background still encouraged renewal, and the Green Sahara regained its balance after generations of uncertainty. During the later transformation, the underlying orbital rhythm had shifted in the opposite direction. Once vegetation retreated and reinforcing feedbacks gathered strength, the humid world no longer possessed the conditions needed to rebuild itself. The earlier pause became a reminder that recovery had once been possible, while the final transition became the moment when that possibility slipped away. Rain alone did not write the story of the Green Sahara. Every blade of grass, every grove of trees, and every wetland stretching across the landscape became an active participant in shaping the climate that surrounded it. The flourishing world was sustained through a partnership between living organisms and the atmosphere, each strengthening the other until they behaved almost as a single system. For many years, climate scientists attempted to recreate the Green Sahara using computer simulations driven only by the gradual changes in Earth's orbit. Those calculations consistently produced a wetter North Africa than exists today, yet the results always fell short. They could not generate enough rainfall to explain immense lakes, thriving populations of hippopotamuses, broad grasslands, or the remarkable rock paintings left behind by people who lived among those animals. The orbital changes were essential, although they could not account for the full transformation on their own. Another influence was amplifying the humid climate beyond what sunlight alone could achieve. That influence was the vegetation itself. A landscape covered with grasses, shrubs, and trees behaves very differently from one covered by pale desert sand. Vegetated ground absorbs a much larger share of incoming sunlight because it has a lower reflectivity, known in climate science as albedo. Instead of sending much of the sun's energy back toward space, darker surfaces retain more heat. The warmed land strengthens the difference in temperature between the continent and the neighboring ocean, deepening the low pressure that pulls moisture-laden air inland through the West African monsoon. Plants also shape the atmosphere through another pathway. Water drawn from the soil rises through stems and leaves before returning to the air in a process called transpiration. Countless plants release enormous quantities of water vapor every day, adding fresh moisture to the lower atmosphere. That vapor helps clouds develop and contributes directly to new rainfall. The landscape was therefore supplying part of the very ingredient that sustained its own growth. Because of this continuous exchange, rainfall across the Green Sahara became a chain of connected events instead of a single journey inland. Water falling over one region soaked into soils and vegetation, returned to the atmosphere through evaporation and transpiration, drifted farther across the continent, then condensed into rain once again. Each cycle carried moisture deeper into the interior. The process resembled a relay, with every stretch of healthy vegetation passing atmospheric water onward to the next. Modern climate simulations demonstrate how important this partnership truly was. Models that omit vegetation feedbacks and the accompanying influence of reduced airborne dust consistently fail to recreate the humid Sahara revealed by geological and archaeological evidence. Once living landscapes and their interactions with the atmosphere are included, the simulations move much closer to the world recorded in lake sediments, fossil remains, and ancient settlements. Biology becomes part of the climate engine itself. The relationship also worked in reverse. As vegetation expanded, it strengthened the monsoon that nourished it. When plants began disappearing, the same connections unraveled. Less vegetation meant brighter ground, weaker heating, reduced transpiration, declining moisture, recycling, and diminishing rainfall. Every loss encouraged the next. The Green Sahara was, in a profound sense, partly self-created through the partnership between life and climate. When that partnership weakened beyond recovery, the same bond carried the living landscape toward its gradual unraveling until both the monsoon and the ecosystem faded together. The Green Sahara that has unfolded through this story can seem like an extraordinary exception, a singular chapter written once and never repeated. The rocks tell a different story. The humid landscape, remembered through lakes, fossils, and human settlements, belongs to a sequence so long that it reaches far beyond humanity itself. The most recent African Humid Period was only the latest expression of a rhythm that has echoed across northern Africa for at least 9 million years. That immense history survives in sediments resting beneath the eastern Mediterranean Sea. Layer after layer of dark, organic-rich deposits, known as sapropels, records repeated intervals when rivers carried enormous volumes of fresh water from a flourishing North Africa into the sea. During each humid episode, stronger monsoon rains nourished vegetation, expanded river networks, and flushed organic material toward the Mediterranean. Between these dark layers lie lighter sediments deposited during dry intervals, when dust once again became the dominant traveler. Together they form a remarkably regular sequence, with many of the wet phases separated by approximately 20,000 years, following the recurring rhythm of Earth's changing orbit. Some of these ancient records can be touched by hand. At the Giblashemi exposure in Sicily, cliff faces reveal stacked sapropel layers that accumulated during the Miocene around 9 million years ago. Each dark band marks another flourishing Sahara from an age when no humans walked the continent, no cattle grazed its grasslands, and no rock artists painted its cliffs. The landscape had already begun cycling between fertile and arid worlds millions of years before the first members of our own lineage appeared. Those earlier green Saharas were never exact copies of one another. Every cycle unfolded within a different planet. Ice sheets advanced and retreated across northern continents. Ocean temperatures shifted over immense spans of time. Atmospheric concentrations of carbon dioxide rose and fell. The plants available to spread across the landscape changed as evolution continued. Each humid period reflected the particular combination of conditions present during its own chapter of Earth's history, even though the orbital rhythm remained familiar. During major ice ages, that rhythm often became muted. Enormous continental ice sheets covering northern latitudes cooled the atmosphere enough to weaken the expansion of the African monsoon. Even when Earth's orbital configuration favored stronger summer sunlight, the chilled climate limited how far seasonal rains could travel. Under those conditions, the Sahara frequently remained dominated by desert landscapes instead of transforming into broad grasslands and lakes. The most recent African humid period unfolded under different circumstances. Large northern ice sheets had largely vanished, allowing the orbital cycle to influence the monsoon with fewer restraints. As a result, this humid interval ranks among the strongest Green Sahara episodes of roughly the past 800,000 years, producing landscapes rich enough to support extensive ecosystems and thriving human societies. Across millions of years, every transition between green and dry conditions left another page within the geological archive. Wind-blown dust settled during arid centuries. Organic rich sediments accumulated when rivers and wetlands returned. Layer upon layer, the ocean floor preserved an almost continuous memory of repeating worlds. The Green Sahara, remembered by people, archaeology, and rock art, occupies only one page within that immense record, a recent verse in a planetary cycle that has unfolded hundreds of times across the deep history of Earth. A desert can appear permanent when measured against a single lifetime. From orbit, however, the southern edge of the Sahara reveals something more fluid. Year after year, satellites record subtle shifts in color, tracing places where vegetation has advanced, retreated, and returned again. The Great Desert has never become completely motionless. Even now, its boundaries continue to respond to changing patterns of rain, temperature, and life. Comparisons between Landsat satellite images captured during the 1980s and more recent observations reveal measurable recovery across parts of the Sahel, the broad transition zone stretching along the Sahara's southern margin. In portions of Niger, Mali, and Chad, grasslands now occupy ground that appeared largely barren only a few decades ago. These changes remain modest when viewed across the scale of the entire desert. yet they are extensive enough to be measured from space. Seasonal vegetation has expanded across landscapes where exposed soil once dominated the view. That recovery extends beyond grasses alone. Shrubs and young trees have returned to locations where local communities had not recorded them within living memory. Their arrival reflects a gradual increase in plant cover that helps stabilize soil, reduce erosion, and create small pockets of shade. Each returning plant contributes another thread to a landscape that had seemed locked into a single condition, demonstrating that even dry environments remain responsive when rainfall becomes slightly more favorable. Part of this transformation appears connected to changes in regional climate. During recent decades, portions of the Sahel have received somewhat greater rainfall than during the severe drought years of the late 20th century. Many climate researchers suggest that warmer sea surface temperatures across the Indian Ocean and the Gulf of Guinea have influenced the strength and position of the West African monsoon, allowing additional moisture to reach some southern margins of the Sahara. The increase has been uneven from year to year, though it has proved sufficient to encourage vegetation where conditions permit. Human effort has also shaped this emerging pattern. Across 11 African nations, the Great Green Wall Initiative seeks to restore degraded land through large-scale planting, improved land management, and support for local farming communities. Millions of trees have already been established as part of that work, accompanied by projects that protect natural regeneration and conserve water within fragile soils. In many places, recovery depends as much on careful stewardship as it does on rainfall itself. Even so, scientists urge caution when interpreting these encouraging signs. The present greening does not signal the beginning of another African humid period. The forces that created the Great Green Sahara operated through gradual changes in Earth's orbit across cycles lasting about 20,000 years. The recovery visible today unfolds across decades, shaped by regional climate variability and human activity instead of the astronomical conditions that transformed an entire continent in the distant past. Its future remains uncertain. A succession of dry years can erase vegetation that required many seasons to establish. Modern climate change also introduces greater volatility into rainfall patterns, bringing heavier downpours in some years and prolonged drought in others. The Sahara therefore occupies another moment of transition, neither fixed nor returning to its former abundance. It continues responding to every subtle shift in atmosphere and land, offering a reminder that even the world's greatest desert remains part of a living climate system whose story is still unfolding. Nothing in the sky has forgotten the rhythm that shaped the Sahara. Earth continues its long celestial motion without pause. The slow turning of precession still alters the direction of the planet's axis, changing how sunlight is distributed across the seasons. That movement unfolds so gradually that no generation can witness it directly. Yet, over thousands of years, it reshapes climates across entire continents with remarkable consistency. Astronomers can calculate that motion far into the future. At the present rate of precession, the next peak in Northern Hemisphere summer sunlight, the astronomical arrangement associated with past Green Sahara episodes, is expected roughly 10,000 years from now, sometime between the years 12,000 and 13,000. Judged only by orbital mechanics, that future alignment should once again strengthen the African monsoon and create the background conditions that have repeatedly transformed the Sahara across millions of years. Viewed through the record preserved in sediments, fossils, and ancient shorelines, this expectation appears entirely reasonable. Earlier, Green Sahara intervals arrived when orbital conditions favored stronger summer heating across northern Africa. Greater heating strengthened the pressure difference between land and ocean, drawing moist air farther inland and allowing vegetation, lakes, and rivers to expand. If Earth's climate system responded only to that repeating astronomical signal, another humid chapter would seem to lie ahead on schedule, following the same enduring celestial clock. The future, however, contains a condition with no close equivalent during previous Green Sahara cycles. Human activity has altered the composition of the atmosphere at extraordinary speed through the release of greenhouse gases. Climate scientists therefore cannot predict with confidence how the next favorable orbital alignment will interact with an atmosphere already transformed long before that distant age arrives. The familiar astronomical pattern remains, yet it now unfolds within circumstances unlike those recorded during earlier humid periods. Even if greenhouse gas emissions ended today, atmospheric carbon dioxide would remain above pre industrial concentrations for many thousands of years. Climate scientist Jessica Tierney has noted that future climate change will be superimposed upon Earth's natural climate cycles, meaning that orbital forcing and human influence will operate together instead of separately. The coming Green Sahara, whenever it arrives, would therefore emerge under conditions that no previous cycle experienced. Clues to such an atmosphere come from a much deeper chapter in Earth's history. Carbon dioxide concentrations comparable to those of today last existed during the Pliocene, roughly 3 million to 5 million years ago. Sea levels then stood many meters higher, which is about dozens of feet above modern coastlines, and global climate patterns differed substantially from those familiar today. That distant world offers perspective, though it cannot provide a direct forecast for the Sahara's future, because orbital geometry, continental ice, oceans, and ecosystems were all arranged differently. Several possibilities remain scientifically plausible. The next humid period may emerge close to the traditional schedule. A warmer atmosphere might strengthen monsoon rainfall beyond expectations, or competing climate processes could weaken that response. Human influence may amplify natural cycles, reshape them, or interfere with them in ways current models cannot yet resolve. The equations describing Earth's orbit remain reliable. The atmosphere, altered by a single species, has introduced a new chapter into a story that once repeated with extraordinary regularity, leaving the distant future open to outcomes still beyond confident prediction. The Green Sahara now belongs to history, yet its greatest value may lie in what it reveals about the future. Across climate science, researchers searching for the behavior of modern tipping points repeatedly return to this vanished landscape. They do so because few natural experiments have been preserved with such clarity. The rise and decline of the Green Sahara left evidence in sediments, pollen, fossils, lake beds, and climate records, allowing scientists to reconstruct an entire system as it approached, crossed, and moved beyond a critical threshold. Among the modern systems receiving the closest attention are the Amazon rainforest, Arctic sea ice, the Greenland ice sheet, the West Antarctic ice sheet, and the Atlantic Ocean overturning circulation. Each contains internal feedbacks capable of accelerating change after a threshold has been crossed. Although every system operates differently, they share an important characteristic with the Green Sahara. Their future depends not only upon the external forces acting upon them, but also upon how the systems respond to themselves. The vegetation feedback that sustained the Green Sahara offers one of the clearest examples. Plants darkened the land, absorbed more sunlight, strengthened atmospheric circulation, and returned moisture to the air through transpiration. That additional moisture encouraged further rainfall, supporting still more vegetation. Once drying became extensive enough, the same relationships operated in reverse. Fewer plants meant less transpiration, weaker rainfall, and additional vegetation loss. The cycle accelerated without requiring a sudden change in the original orbital forcing. A similar process is now being studied within the Amazon rainforest. Trees release enormous quantities of water vapor into the atmosphere through transpiration, helping generate rainfall across much of the basin. As forests are removed, less moisture enters the air, rainfall declines, and remaining forests experience greater stress. That stress can lead to further forest loss, reinforcing the same pattern. The details differ from those of the Sahara, yet the structure of the feedback remains strikingly similar, with biology and climate continually influencing one another. Scientists have also learned that major transitions often announce themselves before the final shift arrives. Studies of the Green Sahara reveal increasing variability in vegetation and episodes of drying that appeared before the complete collapse. These fluctuations acted as early warning signals, suggesting that the landscape was becoming progressively less stable. Detecting such subtle changes has become an important goal for researchers monitoring modern climate systems that may also approach critical thresholds. The mathematical methods developed in the 2025 study from the Technical University of Munich were designed with exactly that challenge in mind. By identifying patterns that preceded the Green Sahara's transformation, the researchers sought tools capable of recognizing similar warning signs in present-day climate records. The purpose extends beyond understanding the past. It aims to improve humanity's ability to recognize approaching thresholds before they are crossed. The lesson carried forward from the Sahara is measured and precise. External change may unfold gradually, while the response of a complex system remains delayed until reinforcing feedbacks gather enough strength to drive a comparatively rapid transformation. Recovery, if it occurs at all, may follow a far slower path than the decline itself. The Green Sahara, therefore, stands as more than an extraordinary chapter in Earth's history. It remains one of the clearest demonstrations that our planet has already experienced. Tipping point behavior, preserving an ancient record that continues to guide the science of today. The story narrows once more, leaving the sweep of climate and returning to a handful of resting places scattered across the sand. At Gobero, the landscape still keeps far more than it has revealed. Nearly 200 burials remain visible across the site, yet according to the most recent published scientific record, only a single disturbed burial has been formally excavated. The rest remain where they were placed thousands of years ago, waiting beneath layers of dry sediment that have guarded them with remarkable fidelity. The same climate that erased the lakes and scattered the people became an unlikely guardian of their memory. Across much of the world, warm soils, moisture, roots, and countless microorganisms gradually return human remains to the earth. Gobero followed another path. As rainfall disappeared and the land hardened into one of the driest environments on the planet, decomposition slowed dramatically. Bones, ornaments, burial positions, and traces of daily life endured because the environment that ended this way of living also prevented it from fading completely. The desert became both ending and archive. Among those preserved objects is a small pendant carved from hippopotamus ivory. It once rested against the body of a woman laid carefully into the ground. The animal whose tusk supplied that ivory lived in a lake stretching across a landscape where reeds, fish, and broad waters supported creatures now impossible to imagine there. Today, that region cannot sustain hippopotamuses. Their remaining populations survive thousands of kilometers away, which is about 1,864 miles, in wetter parts of Africa, where rivers and lakes continue to nourish them. The pendant still carries the memory of waters that vanished long before recorded history. Other objects speak of journeys extending far beyond a single settlement. Beads fashioned from blue amazonite reached Gobero after traveling from rocky outcrops in the Ayer Highlands. The stone crossed hundreds of kilometers, that is, nearly hundreds of miles, through networks linking distant communities across a broad grassland landscape. Those exchanges required trust, repeated travel, and knowledge passed from one generation to another. Long before written maps existed, people were already connected by paths that stretched across a flourishing Sahara. The burials themselves reveal relationships that reach beyond trade alone. One grave contains the remains of a child laid to rest beside two young puppies. The arrangement reflects deliberate care, careful preparation, and customs that assigned meaning to death as well as life. Time was taken to shape the burial. Space was shared between companions whose bond continued after their final breath. Such acts belong to communities able to pause, remember, and express affection even while living within a demanding environment. These discoveries resist becoming mere entries in a scientific catalog. Every skeleton belonged to someone who watched sunlight ripple across a lake, gathered food from fertile shores, exchanged gifts with distant neighbors, celebrated family, mourned loss, and expected tomorrow to resemble yesterday. Their world disappeared as climate shifted beyond the limits that had sustained it. Wind carried sand across abandoned ground until homes, pathways, and graves settled into stillness. The people did not vanish without trace. They remained where loved ones had placed them, and the desert, through an extraordinary turn of Earth's history, preserved their presence until another age arrived to uncover their story once again. There is a measure of time that no clock hanging on a wall can keep. It moves through shifting continents, changing skies, and cycles that return long after every generation has passed into memory. Against that measure, a human lifetime is scarcely more than a passing moment. Every person alive today has experienced only a few decades inside a planetary story that unfolds across roughly 20,000-year rhythms, reaches back at least 9 million years in the geological record, and belongs to a world more than 4 billion years old. Within such brief lives, permanence feels natural. Mountains seem fixed, forests appear enduring, deserts look eternal. The Sahara carries this illusion with particular strength because no living observer has witnessed its full transformation. Generation after generation has inherited broad horizons of sand and believed they were seeing something timeless. Experience encourages that conclusion, yet experience occupies only the smallest fraction of the Earth's memory. The sediments tell another account. Layer after layer, preserved with patient precision, records a landscape that changed again and again. 10,000 years ago, the Sahara was clothed in grasslands, lakes, rivers, and thriving communities. Around 12,000 years from now, if the long rhythm of Earth's orbit continues to guide the climate as it has through countless earlier cycles, conditions favorable for another humid Sahara are expected to return, although human influence has introduced uncertainties that no previous cycle contained. Between those distant moments, the desert itself is revealed as a temporary expression of a living planet, neither permanent beginning nor permanent end. Once that realization settles, the boundaries separating one landscape from another begin to appear less absolute. The Amazon rainforest, the Arctic, sweeping grasslands, and coral reefs each occupy a chapter within longer narratives that continue whether human observers recognize them or not. Their present forms reflect ongoing exchanges among sunlight, atmosphere, oceans, rock, water, and life itself. What seems immovable during one lifetime belongs to processes that never truly stop unfolding. The Green Sahara invites another adjustment in perspective. Nature is often imagined as a stable stage upon which history takes place. Human civilizations rise, flourish, and disappear while the setting remains unchanged. The evidence gathered from buried lakes, fossil pollen, ancient shorelines, and forgotten villages suggests something different. The stage also moves. Rivers alter their paths. Forests advance and retreat. Coastlines migrate. Entire ecosystems emerge, transform, and yield to others without abandoning the larger continuity of the planet. Even the pace of that movement deserves reconsideration. Some changes unfold so gradually that countless generations pass without recognizing them. Others accumulate almost invisibly until a threshold is crossed and the transformation accelerates beyond ordinary expectation. The Green Sahara reminds us that gradual forces can prepare the ground for remarkably swift change. Those who witnessed the final centuries of that transition would have experienced familiar places becoming unfamiliar within the span of ordinary lives. Recovery, when it finally comes, belongs to futures extending far beyond anyone who first endured the loss. Perhaps permanence has never been a property of landscapes at all. Perhaps it has always belonged only to change itself, expressed through rhythms so expansive that human history encounters them one brief moment at a time. Among all the lessons carried forward from the Green Sahara, one stands apart with unusual clarity. It is not the speed of the transformation, although that alone reshaped an entire continent. It is the pattern by which the transformation unfolded. The landscape did not vanish beneath the force of a single overwhelming disaster. No asteroid struck. No supervolcano buried the plains beneath ash. No burst of radiation swept across the earth. The change emerged from within the system itself, gathering strength as one ordinary process influenced another until the balance that had endured for thousands of years could no longer sustain itself. The sequence began with changes so gradual they would have escaped notice within any single lifetime. Rainfall weakened a little. Vegetation became thinner across parts of the landscape. At first, those shifts reflected the slow rhythm of Earth's orbit, a pace measured across many generations. Yet each patch of disappearing grass exposed brighter ground that reflected more sunlight. Less vegetation returned less moisture to the atmosphere through transpiration. Fewer clouds formed. Rain became less dependable. Every change strengthened the next, turning modest decline into accelerating transformation. The living fabric that had helped maintain the monsoon gradually became part of the process that unraveled it. This pattern belongs to a larger language spoken throughout the climate system. Feedback loops appear wherever one change alters the conditions that produced it, either weakening or strengthening what follows. Some stabilize the planet, others amplify disturbance. The Green Sahara reveals the latter with unusual completeness because the evidence survives in so many different forms, from buried shorelines and fossil pollen to marine sediments and carefully arranged graves. Together, they preserve an entire sequence, allowing scientists to reconstruct not only what changed, but also how one change encouraged another. That same structure is being examined across the modern Earth. As frozen ground in northern regions thaws, methane enters the atmosphere. Additional methane strengthens warming, encouraging further thaw. Across the Arctic Ocean, shrinking sea ice exposes darker water that absorbs more sunlight, raising temperatures and reducing even more ice. Within the Amazon rainforest, widespread forest loss reduces transpiration, diminishing regional rainfall and placing additional trees under increasing stress. Although each system possesses its own history and complexity, the underlying architecture remains familiar. A small push can become a larger one when reinforcing processes begin to work together. The Green Sahara, therefore, offers more than an account of a vanished environment. It provides one of the clearest demonstrations that self reinforcing climate change belongs to the real history of the Earth. Long before scientific instruments existed, the planet had already passed through an episode in which gradual forcing produced a response that accelerated beyond the pace of its original cause. The collapse unfolded more rapidly than orbital change alone would have predicted because the landscape itself became an active participant in its own transformation. That experiment ended about 5,500 years ago. Its results remain preserved in ocean sediments, ancient lake beds, weathered stone, and the resting places at Gobero. The record has waited through millennia without changing its testimony. It asks for no belief beyond careful observation. It offers no accusation. It simply shows what can happen when a living system crosses a threshold and begins to carry itself toward a different world. There is a sentence found in scientific literature that seems almost too simple to carry the weight placed upon it. It describes no battle, no empire, no invention. It speaks only of movement across a changing landscape. The gate was open when the Sahara was green and closed when deserts prevailed. Within those few words rests a story measured across tens of thousands of years, one that reaches far beyond the boundaries of Africa and into the ancestry of nearly every person alive today. Climate scientists at the University of Helsinki chose that phrase to describe one of the great consequences of the Green Sahara cycles. During humid periods, the broad desert that now separates northern and central Africa became a connected belt of lakes, rivers, grasslands, and woodlands. Animals followed expanding vegetation. Plants spread with changing seasons. Human communities moved through regions that would later become almost impossible to cross. The Sahara ceased to function as a wall and became a passage, allowing populations to travel in multiple directions while exchanging knowledge, customs, tools, and genes across enormous distances. Those opportunities appeared only during particular intervals. The humid phases depended upon orbital conditions that strengthened the African monsoon, yet those favorable conditions could still be weakened by the presence of immense northern ice sheets. During ice ages, colder global temperatures limited the northward reach of seasonal rains, even when orbital geometry might otherwise have supported greener landscapes. The migration corridor therefore opened only during specific combinations of orbital timing and global climate. Human journeys across Africa were linked to rhythms, unfolding far beyond any horizon visible to the travelers themselves. This pattern left lasting marks upon the human family. Some populations expanded northward through the restored savannah, eventually reaching regions that connected Africa with Western Asia. Across many generations, descendants continued outward into Europe, deeper into Asia, and, much later, into the lands that would eventually be known as the Americas. Other communities remained within Africa, adapting to changing environments while maintaining exchanges with neighboring groups whenever the landscape allowed. Every successful movement depended upon conditions that would never remain unchanged forever. The final Green Sahara marked the last great opening of this corridor in the recent human story. As rainfall diminished and vegetation retreated, Familiar routes disappeared beneath growing expanses of sand. Lakes contracted, rivers failed. Communities adjusted by following dependable sources of water, including the Nile Valley, where concentrations of people contributed to the rise of one of history's greatest civilizations. Elsewhere, movement across the continent became increasingly difficult as the returning desert established a barrier that would persist for about 5,500 years. Modern maps often encourage the impression that continents possess fixed pathways and permanent frontiers. The deeper record offers another perspective. Gates within the natural world are created by climate, sustained by climate, and eventually withdrawn by climate. They shape encounters between populations, determine where species can spread, and influence which cultures meet or remain apart. The rhythm of the Sahara belongs within that larger pattern. Every opening altered the possibilities available to countless generations. Every closing redirected the course of lives that would never know why the path before them had changed. In that sense, the pulse of the Sahara became woven into the unfolding story of humanity itself. Somewhere within Niger's Tenere Desert, beneath layers of pale sand shaped by thousands of seasons, a child still rests beside two young puppies. Their embrace has remained undisturbed for roughly 7,000 years. No monument marks the place. No path leads visitors across the dunes. Time itself has become the guardian of that small burial, preserving a final moment of care from a world that no longer exists. The lake beside which they were laid to rest has vanished. The grasses that once bent along its shore have disappeared. The giraffes that wandered across the nearby savannah are gone. The rain that sustained every living thing has long since withdrawn. Even so, traces of that vanished landscape remain. The bones endure. Harpoon points, fashioned by careful hands, still rest where they were left. Paintings survive upon sheltered stone, carrying echoes of lives once woven into a thriving land. In one of Earth's quiet ironies, the desert preserved the very world whose disappearance allowed the desert to exist. The memory extends far beyond the ground itself. Seen from orbit, instruments capable of looking through dry sand reveal channels carved by rivers that have not flowed for thousands of years. They appear as faint patterns stretching across the modern Sahara, hundreds of ancient waterways recorded in radar images with remarkable clarity. Their courses still cross the desert, following paths shaped by water that once gathered from seasonal rains before finding lakes and wetlands scattered across the continent. The landscape remembers even after the rivers have forgotten how to flow. Above those enduring marks, the planet continues its patient motion. Earth's axis still wobbles through space. The cycle of precession has never paused. The same orbital rhythm that helped create the Green Sahara, then guided its return to desert, continues as it has for at least 9 million years. It will continue long after every city, monument, and road built by humanity has weathered into the rocks from which they first arose. The clock has never hurried. It has never fallen behind. Roughly 10,000 years from now, the geometry of sunlight is expected to favor another strengthening of northern hemisphere summers. The West African monsoon may once again push farther inland. Rain could return across lands that have waded through many thousands of years of dryness. Grasses would likely appear before anything else, followed by shrubs, scattered trees, expanding wetlands, and lakes gathering once more in familiar basins shaped by countless earlier cycles. The sequence has unfolded many times before, each chapter carrying its own character while following the same enduring rhythm. No one can know which creatures will stand beside those future waters. Hippos may belong only to memory by then. Giraffes may follow different paths, or none at all. Other lives will arrive instead, shaped by climates and histories still unwritten. They will drink where deserts once stretched beyond every horizon, in a place that has alternated between abundance and dryness across millions of years, long before humanity appeared to witness the pattern. The Sahara is often described as empty. Its deeper story suggests something different. Nothing about this landscape is fixed. Beneath the sand rests the memory of rivers, forests, animals, and people. Above it, the heavens continue their measured turning. The desert has never stopped changing. For now, it waits, carrying every earlier world within itself, until the sky, once again, invites the rain.